Okie doke. Today we're going to talk about, give the second of two talks on electronics. I'm going to make sure I got the camera right here because I gave this talk once and then for some reason it was out of focus. I'm hoping that doesn't happen again. Looks pretty good there. So today we're going to give the second of two talks on electronics. And this whole lecture is going to center in on the electronic computer. A computer is a device that processes information using electronic circuits. That's to distinguish a computer from something I'll show you in just a minute, called mechanical calculators or mechanical devices that also process information, but do not use electronic circuits. They use physical circuits. One of the reasons that early on computers were difficult is shown in this picture. You see all the cords and cables and wires, and there was a lot of wiring that was necessary to do the kind of things that they wanted to do with computers. Now, computers handle what's known as data. Data is individual pieces of information. Data can come in the form of text, it can come in the form of numbers, it can come in the form of various other types of responses, light signals, sounds, etc. So anything that's would be considered a stimulus of some sort can be data depending on the context. Computers are valuable for one big reason. They have a great capacity for processing enormous amounts of data accurately and quickly. Computers were essentially developed initially to do repetitive calculations that were not necessarily difficult to do, but were mind-numbingly boring. And the computers were developed so that it would decrease the number of mistakes and the amount of time necessary to do those things. Nowadays, computers can perform literally billions of calculations per second. Now, the computer you're looking at here is not capable of that kind of speed. But the computers these days can do a huge number of repetitious calculations very efficiently and very quickly. And that's the value of a computer. Now, some mechanical means of calculation, before the electronics were applied to calculating machines, the mechanical means, the earliest and simplest of the mechanical means was called an abacus. This was a simple counting and calculating device that was made of beads. And this is what it looked like. You can see that in this abacus you have several rows. I think there's 10 rows, and each row has 10 beads. And the reason that each row has 10 beads is because of the base 10 system that we operate on, or the decimal system that we operate on. And you slide beads back and forth, and by doing that, you can do simple calculations. Now, the abacus is limited primarily to add, subtract, multiply, and divide. The other forms of calculation you cannot do on an abacus. But if done correctly, it gives you very accurate results. The device that I used to use when I was in high school is called a slide rule. A slide rule was a common calculating device used in the 60s and 70s. It was very accurate. It required some training to learn how to use it. But if you learned how to use it, you could do many very difficult and complicated calculations using a slide rule. Now this one's a little bit more complex slide rule, but some slide rules are actually quite simple and you can just do add, subtract, multiply, and divide. The slide rule that I had was much more like this one, and with that slide rule you could do sine, cosine, tangent, you could do logarithms, and so the slide rule was a step up from the abacus in that regard. As I said, these are mechanical calculators. These calculators are devices like slide rules and an abacus that they perform calculations using a mechanical rather than electronic means. Now the first computer was called an ENIAC, which stood for Electronic Numerical Integrator and Calculator. This is the first computer that was created. It was invented in 1946, so you can mark that as the date the first computers were made. So it was exactly 70 years ago that this first generation of electronic computers came into being. Now the ENIAC was a very complex, cumbersome machine with very cumbersome cords and dials and bells and all kinds of circuits, primarily because we didn't have a lot in the way of electronics. The ENIAC did not have, it was mostly wiring as opposed to electronics like vacuum tubes and diodes and so forth. Mistakes and bugs that were found in the ENIAC led to the development of the next computer, which was the UNIVAC-1, which stood for Universal Automatic Computer. This was developed primarily from learning in creating the ENIAC. And this computer worked well enough that it was actually mass produced and used in many different places. Now, one of the things about computers back then is that they were so big and heavy, they had to be put in the basement of buildings. The electrical wiring was so complex and there was a lot of heat involved, so there had to be ways of cooling it. And so it was very difficult to actually find places where you could put together a computer. All that being said, though, here's a picture of the UNIVAC-1. All that being said, though, these were both major advances in the world of calculating machines. Now, once the ENIAC was made, and it's represented down here at the bottom of this tree, then the advancements beyond the ENIAC served three purposes. Two of those purposes are here. From this point forward, the goal was to make the machine smaller and faster. Better electronics led to the ability to make the machine smaller and faster. Now the third thing was more efficient or easier to use. And so all of the advancements that occurred after the initial ENIAC machine and the UNIVAC-1 were advancements that either reduced the size of the machine, increased the speed of the machine, made the machine more user-friendly, or a combination of those things. And as time passed and the electronics became better and better, these various goals were accomplished. And the reason for that is that even the most complex computers are based on simple circuitry. In other words, every operation is an extremely simple operation, and complex things that are done with computers are accomplished by dividing those complex tasks into multiple or hundreds of simple tasks, and then executing those simple tasks extremely fast and extremely accurately. And so because of the simplicity of the underlying circuitry, the The idea was to develop wiring and electronics that would allow for speedy, lightweight, easy to use ways of accomplishing these goals. Now, data essentially comes in two forms. Data can come in an analog form, and the analog data is data that can have any possible value within a specified range. And the clock here is an analog clock, and this is an analog sound wave. And you can have any value within the range of that wave. You can have any value of data within the range of that wave. On this clock, you can have any value in terms of what the clock can say. The other type of data is digital data. And digital data can only have certain values within the range. And what you see is the digital wave has these steps. And so there's no way of expressing a data point in between a particular step. There's no way of expressing data points on this digital clock that is not a whole second. In other words, you can't specify halves of seconds or quarters of seconds. On an analog clock or on an analog wave, you can express halves, quarters. Now, you may not express them very accurately, and you may not be able to figure it out looking at it, but the fact is that an analog data point can be anywhere on that wave. A digital data point can only be on the plateaus of each of those wave steps, and it can only be in the numerical value seen on the digital clock. Now, because of the electronics involved and because of the way the computers speak to each other and do their computations, the data that's inputted into a computer is digital data. It has to have a certain value, and I'll show you how that works. It is not possible for computers to take in any value of data or read out any particular value. Now, the certain values can be very accurate, can be very precise, but once that level of precision is determined, it cannot be made more or less precise. Now, in order to understand how computers work, you have to understand how computers convert, or how digital data or text data or various types of data is converted into electricity, for lack of a better way of saying it. And in order to do that, the numerical system had to be changed. The numerical system that most civilizations run on, and the United States runs on this, Europe runs on this, is the numerical base 10 system. A numerical base 10 system has 10 values, 0 to 9, and then when you reach the next value, it's a combination of the previous 10. And it works every 10, it changes and has another combination. Now, computers, on the other hand, work on a binary system, a system that is powers of 2, where all the values have to be either a 0 or a 1. And the reason for that is, if something is a 0, it can be an off switch. If something is 1, it can be an on switch, because electronic charges are either on or they're off. There's nothing in between. And so this binary system, each individual binary value is called a bit, which stands for binary digital. And so data can be translated or represented in circuits on digital computers by either the presence or the absence of pulses of electricity. And so if the value is 0, the electronic system is off and the charge is off. If the value is 1, then the electronic system is on. And so in this way, you can translate a numerical value into an electrical impulse. Now, the actual smallest directly accessible unit of data, because of the way it has to be read into a computer, is called a byte, B-Y-T-E. And a byte is made up of 8 bits. And so this is an example of a byte. Say this might be the number 5. The number 5 can be represented in a binary system on a computer as 1001111. This would then be translated into an electrical circuit as a on, off, off, on, off, off. And so in this way, a number or a letter of text can be translated from the number or letter into a binary byte, and from that into electrical impulse. Now, in order for us to read it, we have to use something else called the hexadecimal system. The purpose of the hexadecimal system is to allow humans to read the data, because binary data is virtually impossible for humans to read. And it looks like this. What you have on the left, is the decimal system. On the far right is the binary equivalent of those decimal numbers. And in the middle would be the hexadecimal equivalent of those numbers. And so in the computer, the decimal zero might be represented as 4 zeros or 4 offs. The number 1 might be represented as 3 zeros and a 1. Actually, in order to make this simple and fit in this table, they're only using 4 digits. It would actually be 8 digits in a real computer, because that's the way they do bytes. Now, in order to translate the bytes into something that can be read, they developed a code. And that code, the initial or common code, was called ASCII. ASCII stands for American Standard Code for Information Exchange, which is the most common coding system used to transfer numbers and symbols into binary language. So it's a code that translates or converts numbers that we can read and symbols that we can understand, like letters, into binary language. And this is what that looks like. And you can see it's fairly complicated, but each symbol on the right half of this table has an equivalent value on the left side, binary value, and also has a hexadecimal value. And so this would be one example of an ASCII code chart. And it's the combination of the 4 digits on the left, and then across the top, the digits you see across the top. Now, a more complicated but easier to read system for humans is called the Unicode Standard. Now, the Unicode Standard uses 4 bytes or 32 bits of information of area to store each character. Now, the reason that we were able to do that is because the ability for computers to handle more and more information increased as the electronics became better, and so it was possible to use more and more to designate each symbol. And this is what that looks like. And you see there's a lot of various interesting little symbols that represent different information. Nowadays, most computers use the Unicode standard on the right and not the ASCII system on the left. Although, even now, you can translate a text document or some other amount of data into ASCII if you want to. Now, when we talk about data and when we measure data, we use Systems International prefixes that we're familiar with in order to describe amounts of data or measuring computer data. Now, because it's in the base 2, the value is slightly different, or the meaning of each is slightly different. If we say a kilogram, we mean 1,000 grams. If we say a megagram, we mean 1,000,000 grams. However, when we say a kilobyte, what we mean is 1,024 bytes. And the reason it's 1,024 instead of 1,000 is because we're working in base 2 instead of base 10. And a megabyte, which is 1,000 kilobytes, is actually 1,048,576 bytes. And you can see that each of these has this slight variation from the standard decimal system. Now, in addition to the language and the use of bits and bytes, we also have something known as logic gates. A logic gate is a device that produces one single binary output from a combination of results. So a combination of diodes, a combination of transistors, or a combination of other components. So, for example, let's take this one right here, the one in the top left corner here. And you see the word AND there. So you might have on one resistor or one transistor or diode the letter A, the other one's the letter B. If A is 1 and B is 1, both of those are positive. With the symbol AND, then AB is positive, and it will be a 1. However, if A or B are negative, if A is positive and B is negative, or A is negative and B is positive, then AB is a 0. Also, if both of them are negative, then it's a 0. Now, sometimes if both of them are negative or both of them are positive, then AB is positive. But usually, both of them have to be positive in order for AB to be positive. So that's the AND logic. The OR logic, it means that for AB to be positive, then A can be positive or B is positive, or AB is positive. And the only way that OR is negative, this side is negative, is if both of these are negative, both of them are zeros. And so by using these logic gates, so AND means it's true if 2 bytes are true. So if both A and B are true, then then the 2 bytes are true, then the combination is true. OR, on the other hand, is true if one or the other of the bytes is true, or both can be true. So by using combinations of logic gates, this allows the computer to form a variety of mathematical and logical operations. So this expands the ability of the computer to do these sorts of things. Now, when we talk about computer hardware, there are 3 types of computer hardware. By the way, the hardware is the actual physical components of the computer. It's the things that you carry into your house and set up. And these basic systems can be divided into 3 parts. It's either processing, memory, or input-output devices. Processing are the things that do the calculations or computations. In most computers, you have what's known as a central processing unit, or CPU. This is a device that controls all the other functions of the computer. And so it's essentially functions as the brains of the computer. Now, as electronics became more and more sophisticated, you could get more and more into a single chip, and to the point where you could put an entire processing unit in one microchip, which is what is shown on the slide here, and that's called a microprocessor, when you can put all the computer power or all the processing power in one chip, like this chip right here, then that's called a microprocessor. Now you can also put more than one processor or more than one CPU together and link several chips together in one big chip, or in one big aggregation of chips. And when you do that, that's called a multi-core processor. And this just shows an example. You have processor 1 and processor 0, and inside each of these is 2 CPUs. And so you have a total of 4 CPUs and 2 multi-core processors, all of which draw from a single memory system. And the computations that are done can be integrated after they are performed. Now when you process, or when you have more than one processor operating at the same time, it generally divides the processes between the several CPUs that are available, and that is called working in parallel, or working simultaneously. It's called parallel processing. Another name for it is multiprocessing, because obviously they have more than one processor going on at a time. So as I said, the first group or subtype of hardware is the processing. The second type is memory, and there are a lot of different kinds of memory. One type of memory that you hear a lot about is called RAM, or random access memory. This is the storage memory, the working memory of the computer, where information is stored on a temporary basis. It's stored there for immediate use, and then it's erased after it's used, and then something else is stored there. This is just an example, shows you have random access memory on the left and read-only memory, which I'll talk about in just a second, on the right. There's also multiple subtypes of random access memory, so don't get bogged down in that. Now this actually is very helpful if you concentrate on this for a second in order of understanding how this works. Let me see if I can sharpen this up just a little bit. No, that's about as good as it's going to get. Whenever we do things as humans, we bring things out of our long-term memory into our working memory. And in our working memory is where we do computations that are right in front of us. Then after we finish whatever we're doing, we tend to forget this, or we bring something else into the working memory. This is analogous on the computer to the RAM, which is temporary storage, and more permanent or mass storage on the below that, on the right here. So the computer can get material, data, whatever, out of the mass storage or permanent memory and bring it into the temporary memory area for work. Then it erases that. This is not removed, but it erases it, and it'll bring something else in here to do a different calculation. Obviously, all of this is happening at warp speed. I mentioned on the last slide something called read-only memory. And read-only memory is a very small amount of data that's stored on the computer, that's basic information that every computer has to have in order to start and operate. But the third type of memory is the mass storage, and it represents the permanent storage area of memory on the computer. It's for long-term storage, and it generally holds significantly more data than the random access or temporary memory. Now there are several types of mass storage data that's available, or mass storage devices that are available. The one that you probably heard about the most, that had been talked about the most, is called the hard disk. They always say when you buy a computer, your hard disk, you have a 2 gig hard disk, which means your mass storage is 2 gigabytes of data. Or you'll have a 10 gigabyte hard disk or a 50 gigabyte hard disk or whatever. This is the most commonly used mass storage device. And basically it can be made up of two things. The older type is a series of spinning disks that can be read with a read-write head. And the reason this is the older form is it's more fragile. And it's been replaced, particularly in some of the smaller Apple computers, by something called solid state memory, which is not spinning disk, but single chips that the data is stored on, and then the read head just travels over top of these chips and picks the data up from that. The reason is that the spinning disks are have to be aligned exactly right, and if something happens to your computer, you drop it, different things that happen, and it gets out of line, then the hard disk can't be read, and you can lose your data. And so that's why they've moved to a more solid state type system. If you have an older computer, you can actually hear the hard drive disks spinning. They'll stop and then they'll start spinning again when the computer needs more memory. Now, another storage device is called an optical disk, and the optical disks used to be very popular because they were capable of holding a huge amount of data. The way they store the data is a series of microscopic depressions on a flat surface that is then read by a laser. And again, these depressions are made by either a 0 or 1. It's the same sort of system that you see throughout the computer. So here's an example of an optical disc. Inside the disc is a laser-like aperture that can fire a laser and read the data off of these CDs. The third type of storage is called a flash memory. A flash memory is essentially a card like the solid state memory I was talking about before that can be plugged into your computer. It can be used repeatedly and erased, reformatted, and these are what some people have called memory sticks. And here's an example of flash memory that's plugged into a USB port, and these can have sizes, fairly large sizes, as these have become better and better. And so these are all different forms of long-term memory or mass storage memory. You can unplug this and carry it with you, plug it into a different computer. It's much more mobile. The optical disc can't be carried. The discs can be carried. But if you're going to use this, you have to have a computer that has an optical reader. The hard drive is the least mobile and is pretty much confined to that single computer, whichever computer has that hard drive in it. So as you go down this list, you see more flexibility, more portability, which is a very useful thing. This slide shows some of the third type, which is the input and output devices. And you see on here various input and output devices. The most basic, the earliest, the most common input device that's still commonly used is the keyboard. The keyboard inputs text and numbers and commands. An example of the keyboard's right there. There's also a keyboard on most notebook computers. Essentially, you use this to input various commands into the computers. It used to be that you had to tell the computer what you wanted it to do based on a series of three-letter or letter number commands that would, like DEL meant delete. I'm trying to remember some of the old commands I used to use, but the only one I can remember is DEL, which means delete. And then you, beside that, you would put what you wanted deleted. It was all typed in. Well, now, or as time passed, the next device, input-output device, primarily input device, was the pointing device, what we call a mouse. This revolutionized input into a computer because it made it much easier than typing in the commands. So you could select commands from a menu and just point at the command, like the delete command or the cancel command or the print command, and you just clicked it instead of having to write PRT, which was print, or DEL, which was delete. And then you could also select text that you wanted to copy or delete or do something with. So the mouse was a significant step forward in terms of input into the computer. Other input devices include input would be the scanner. You could scan documents into the computer. The video camera, you can video into the computer. I'm not sure there's a picture of it here, but you can also use a microphone and input audio into a computer. Now, in terms of output, the earliest and most important output device is the monitor, which is shown right here, and is right here. Now, other output devices include printers and speakers for sound. And so you basically can transfer or output various different kinds of outputs using these various input and output devices. Now, in order for a computer to communicate with another computer or another computer system that's not directly wired to it, you had to be able to change digital information or data into analog information. Then that analog information was transferred over a telephone wire, and then it had to be transferred back into digital information. And the machine that did that is called a modulator demodulator, or modem for short. And so what this allowed you to do was to be able to communicate beyond your home through the telephone or various other means. Initially, you had to take the receiver off the phone and put it on a stand that had a hole for where you put your ear and a hole for your mouse speaker, and it would communicate through that. It would make a series of noises that was part of the conversion of data from digital to analog and back. Then as it advanced, you were able to plug the telephone line directly into your computer without the handset, and then ultimately it became wireless. This is a modem, and in one jack you would put your computer line into your computer, and the other would be a line into your phone, would be your phone line. And so the analog information would come in through the phone line, be converted in here into digital information, and go out into your computer, and then the reverse, like that. Modems were very important to communicate outside wherever the computer you're using resided. Until they developed the modem, there was no way for a computer to communicate with another computer or outside of the area that you were in. Putting all this together is the motherboard. The motherboard is a circuit board that contains the processors. It contains some of the memories like the hard drive and the RAM and the ROM. Many times it contains a modem card. Many times it contains a video card that translates the information into a video signal that's sent to your monitor, and it looks something like this, so that your CPU may be this guy right here, and then some of these things down here might be your RAM, and then another place might be the hard drive, etc. And this just is a circuit board that allows for all this to be wired together. Now that was all hardware. Now we're talking about software. And software is any program that directs the operation of the computer. So it is the instructions, if you will, that tells the computer what to do. And basically software comes in two forms. You have what's called the system software, which is the programs that are the sort of underlying fundamental or basic operations of the computer, called the operating system. And then you have the application software, which is the programs that do user tasks. Now the symbols you see up here represent mostly or all user tasks or application software. So you have the Word software, this W here, that's a word processing program. The P, which stands for PowerPoint, which is a presentation software. N, which is Note, which is a note-taking software. This symbol right here is for Chrome web browser, so it's a web software that allows you to browse the web, which we'll talk about in a second. This is Firefox, which is another program that works on or allows you to browse the web. So let's talk about how this software is brought together. It has to use code in order to communicate or change human instructions into computer instructions. And so one box represents the machine language, which is this language here. And the machine language is the form in which a program is written so the computer can understand it. The other language is the programming language, which is over here. This is the part that humans understand. And so these have to be linked together in order to be able to translate whatever problem or thing you want to do into a program that will do it, into a machine instructions that will actually execute it, and it happens. Now the modem gave us the opportunity to communicate across space. And when you put more than one computer together, you create what's known as a computer network. A computer network is two or more computers that are linked together to work together, or they work off the same information or data. Now there's essentially two types. There's a local area network, or LAN, which is circumscribed within a particular physical area. Companies frequently will use a local area network because of security, in order to prevent people from the outside being able to get in and get on their information. The company I work for has what's called a local area network, and I have to be able to log into that network. Once I'm in there, then everything is secure from the outside. And then the second network is the more global network that's shown here. And that is called the internet. The internet is essentially a means of attaching multiple computers together over large distances. And there was a lot of things that had to be accomplished in order to do that. There are various different networks that this happens in. The World Wide Web is just one of those. You may have heard the term darknet, that's another one. Now, cloud computing is just a subtype of the internet, in that what they do is they put together several of these machines here, which I'll talk about in just a second, and then in those they'll have memory, programs, various other things, and you can access that memory and those programs from the internet so that you don't have to necessarily have the program or the data on your computer. You can keep it at a remote site, so that if your computer is stolen, your house burns down, or it allows you to use programs without necessarily installing them on your own computer. There's actually one computer that's made by Google that's entirely a cloud computing system. In other words, there are no resident programs on the computer. It goes online and it uses all the programs online in the cloud. It's called a cloud. It's not really a cloud. It's actually, let's talk about the next one. I'll show you what it is. It's actually a group of servers. A server is a computer that can be accessed by many users at the same time. And it can function as a mass storage device, a hard drive, and in which case it's called a file server. It's a place to store memory. Or it can be a site for email traffic where multiple can go. It can also be a place where you can do various things, like on Google, for example, they have a word processing program called Google Docs. They have a presentation program. They have spreadsheet programs. So the servers can do just about anything now. This is an example of several servers together, which they call server farms. And I've been told that the Google server farms are enormous, covering many square miles of area and having memory capacity of virtually unlimited memory capacity. Now, another type of computer that we don't use very often, but is used by large companies, is called a mainframe. And a mainframe computer is a large computer that has a lot of capabilities. It's like a very large, complex version of your laptop or your desktop. And if you go for the biggest ones, they're called supercomputers. Supercomputers are large, and now when you talk about large, because of the technology, you're talking about machines that can do literally giga or terabytes of calculations at a time. And this is just one example of the Titan supercomputer. Supercomputers can be used to do simulations that are just not possible in the old days. They use supercomputers to estimate the motion of molecules around a propeller, to do things that require literally trillions and trillions and trillions of calculations per second. I'm going to finish up here with a couple of practical uses of computers. There are obviously more practical uses than what I'm going to talk about here. On the left, you have a schematic, a simple schematic for any-like brake system. What an any-like brake system does is it senses, here a sensor is an input device. It senses the speed in which these wheels turn and the pressure involved, the speed of the vehicle and the speed with which the wheels turn. And if there's a disconnect or a discordance between those two, it will manipulate the master cylinder in such a way as to prevent the wheels from locking. And so there's a computer in here that takes this data and feeds it into the system and tells it to unlock so that the brakes don't lock. Another common application of computer science is on this side, the various robots. The ones I have here are industrial robots. They can pick up and move materials from table to table. They can operate welding machines. They can do inspections. They can do, in a laboratory, you can set up a robot that will do a series of repetitive pipettings or various other things in order to accomplish your tasks. So that's the end of this lecture, and what I would like to say before I sign off here is that next week I'm going to try to put together a talk on the various theories behind the origin of the universe, because I think finishing up the year with something interesting like that would be worthwhile. Thank you very much.